Alright, so today in this video we're going to be talking about resonance structures. Well, what really are resonance structures? What does it mean to be resonance stabilized? Because we hear that term often in organic chemistry and even general chemistry. So let's kind of dive into this. We know that we like to represent organic compounds as bond line structures. The bond line structure, of course, is just a line structure where each corner represents a carbon, and each carbon fulfills an octet. So when you see nothing attached to each corner, we know that hydrogens are attached. So this would have 3 because carbon has 4 valence electrons. This one here would have 2. This one here would have 2. And this guy over here would have 3. Okay, so the thing with bond line structure is there's a significant problem. A pair of bonding electrons is always represented as a line between 2 atoms, which has the implication that the bonding electrons are confined to a region of space directly between those 2 atoms. So a correct depiction would be the case of this molecule here. See, when we have the pi bond in between these 2 central carbons, we know that all the electron density is just going to be in between those 2 carbons. So that's valid. That checks out. But there's other examples where electron density is spread out over a larger portion of the molecule. Let's take a look at this molecule here, for instance. This is called a carbocation. So in this molecule here, we have a positive charge on this N carbon. So this gives us an idea that it's deficient in electron. So if this is deficient in electron, I don't know if we can really say this is the whole picture. So let's investigate this molecule. We have 3 carbons. This carbon here, this carbon here, and this carbon here. This carbon right here is sp2 hybridized. This carbon here is sp2 hybridized. Why can I say that it's sp2 hybridized? Well, it has a pi bond, or the carbon has a pi bond attached to it. So we know there must be 2 hydrogens attached. If there's 2 hydrogens attached, that leaves us with 1, 2, 3 electron groups. So that would give us our trigonoplanar geometry. And we know that trigonoplanar is sp2. So that's okay. That's something. This carbon right here is also attached to the pi bond. So it has 2 hydrogens attached. So if this one has 1, 2, I'm sorry. Let me just grab my eraser here. It has 1 hydrogen attached because it has this other, it's attached on this side as well. But that leaves us with our sp2 hybridization. We have 1, 2, 3 electron groups. So this one is also sp2. Now let's look at this final carbon over here. This final carbon is deficient 1 electron. So we know that it's going to have just 2 hydrogens. So it's not that it doesn't have that p orbital. The p orbital is just empty. These two carbons have p orbitals, but this p orbital is actually empty. But we can still say it's sp2 hybridized. So basically, if we were to look at this kind of like three-dimensionally, we would see we have our carbon here, we'd have our carbon here, and we would have our other carbon right here. We said this one has 2. This one over here also has 2. Or no, this one has 1. And this one here has 2. So since they're sp2 hybridized, we know it's going to have a p orbital. P orbital is dumbbell shaped. This one as well is going to have a p orbital. This one here is going to have a p orbital that is empty. So since all these are trigonoplanar, that means the surface of this right here is all in the same plane. Definitely not a perfect plane, but I think you get the idea. Okay. So let's focus our attention to this continuous system of p orbitals that was just laid out. It functions as a conduit, or kind of as like a pipe. Think of it as a pipe, allowing 2 pi electrons to be associated with all 3 carbon atoms, so the electrons can flow. Valence bond theory is not going to settle for this case. VB theory fails. So you might ask, why would it fail? Well, it's inadequate for this analysis of this system because it treats electrons as if they were confined between only 2 atoms. That would have been fine for that first case that we talked about. Valence bond theory would work here, but that's not the case with the carbocation we're working with. So what we need to consider is molecular orbital theory, MO theory. So what is molecular orbital theory going to do for us in this case? Well, we're gonna be able to treat the whole molecule as one entity. So whole molecule is treated as one entity. So that's really important to get your head around for this topic. So all the electrons in the entire molecule occupy a region of space called molecular orbitals. So according to the molecular orbital theory, the 3 p orbitals are replaced by 3 molecular orbitals. And these are all in order of increasing energy. So we basically have three bonding molecular orbitals, and we'll start with the lowest energy molecular orbital. So lowest energy molecular orbital. Just put MO for short. So we look at our molecule. We have our carbon. We're just going to draw them as circles. We're going to have our 2 hydrogens. We have this carbon over here with we got our 1 hydrogen here. Then we had the last carbon, and that had 2 hydrogens. So this orbital has no vertical nodes. So it's going to look something like this to represent the space. So something like that. All right, let's go to another page. So that's the lowest energy orbital. Next up, we have what is called the non-bonding molecular orbital, and it has 1 vertical node. So this one looks, we draw the molecule again with circles, hydrogen, hydrogen, carbon with 1 hydrogen, and the last carbon, which has 2 hydrogens. Sorry, we know hydrogens are small, of course. That's why I tried to draw this hydrogen atoms smaller than the carbons. Okay, so this one has actually 1 vertical node. So it's going to look something like this. Okay, and this is kind of the middle guy of energy, not lowest, not highest. So that leaves us with the highest energy one, which would be the anti-bonding molecular orbital. So if the non-bonding molecular orbital had 1 vertical node, you kind of guess the anti-bonding molecular orbital is going to have 2 vertical nodes. So this one, just draw this molecule one more time. It's going to have 2 vertical nodes. So it looks something like this. All right, so this one has highest energy because it has 2 vertical nodes. Okay, so the pi electrons of this, we're going to call it an allyl system, because it has this pi bond next to the deficient electron site, and that's called allylic when it's next to a pi bond. Vinylic means when it's attached to a pi bond. So the pi electrons of this allyl system will fill these molecular orbitals, starting with the lowest energy molecular orbital, which was the bonding molecular orbital. If the missing electron were to return, it would occupy the next higher energy molecular orbital, which would be the non-bonding. Molecular orbital theory suggests that the positive charge of the allyl carbocation is associated with two ends of the system rather than just one end. So chemists use resonance to deal with the inadequacy of bond line structures. We draw more than one bond line structure mentally meld them together. So we're gonna have to kind of think of an analogy for this case, but two ideas that you kind of got to mix together are having the positive charge on the right side, but then at the same time having the positive charge also on the left side. Oops. All right. So these are drawn to represent positive charge spread over two locations. The spreading of electrons, called delocalization, is a stabilizing factor. That is, molecules and ions are stabilized by the delocalization of electrons. The stabilization is often referred to as resonance stabilized. So it really just means, since it actually has the positive charge on multiple sites, it's not just going to be reactive. It's not going to react on one end because it actually has the charge on multiple different ends. So the state now we gotta consider some rules if we're gonna do this right. So when we draw these structures, we have to know so for these structures, we got to know how to draw them to represent them. So what we use to usually draw resonance structures are curved arrows. So a curved arrow consists of a head and a tail. So the end is the tail, and the head is with the arrow. These curved arrows do not represent the motion of electrons. I'll repeat that. These do not represent the motion of the electrons. These the tail shows where the electrons are coming from, and the head shows where the electrons are going. It's kind of just a thing we do to show where the electrons would go if they were moving around. But it's just to show kind of like how to get from one of the places of positive charge to another. So remember, the electrons aren't going anywhere. We're just treating them as if they were for the purpose of drawing the resonance structures. Okay. So we got some rules to follow for using these curved arrows. Rule number 1, never break a single bond. So we're not going to be breaking sigma bonds. Number 2, never exceed an octet for second row elements. So when we say second row elements, we mean boron, carbon, oxygen, nitrogen, fluorine. But there's an important note here, and it's that we can have less than an octet. Okay, so these 2 rules are going to be really important, because if we don't follow them, we're going to be doing our resonance structures wrong. So let's look at an example. So let's ask ourselves, does this arrow violate the octet rule? So let's keep in mind our hydrogens. We have a pi bond here, so there must be 2 hydrogens right here. So if we're removing this, if we're breaking this pi bond to move it over here, this site is already deficient 1 electron, so it just has 1 hydrogen. So it's okay. I mean, it's only, the carbon only has 3 electrons, so if we move another one over, it'll have its 4. It'll meet an octet. So this is good. There's no violation. So we can take a look at another example. So when we're using curved arrows to derive resonance structures, we will often have 1 or more formal charges to contend with. We need to be able to indicate formal charge to draw the valid structure. So let's take a this structure here, for instance. So let's say we wanted to create a formal charge. So what if we move this lone pair right here to this sigma bond? Well, if we do that, we already have 1, 2, 3, 4, because that's a pi bond. So that would be exceeding an octet for this carbon right here. So in order to compensate for that, we would also need to break this pi bond here. So after doing those two bond breakings, we end up with this molecule here. This oxygen has a formal charge of +1. And this carbon here has a formal charge of -1. So, like we said before, resonance structures are representing the molecule at the same time. We think of it as like a nectarine. A nectarine is not just a peach or a plum, but actually both at the same time. A plum, it can have either physical characteristics of a peach, it can have texture characteristics of a plum, but it's really inadequate to say whether it's just a peach or a plum. It's a nectarine. So a resonance stabilized molecule is a resonance stabilized molecule. The resonance structure just possible states of, or just different sites where the charge can be. Okay, so let's make another observation here. We see this has a plus formal charge and a minus formal charge. So we know that every resonance structure has to have the same formal charge. So this one has obviously 0. There's no formal charge anywhere. And this one here has a plus and a minus, which equals 0. So they should always cancel out. So with that in mind, we can go ahead and start tackling some examples. So, well, real quick though, before we get into this, we got to remember our vinylic and allylic positions, and we got to know the patterns for drawing the resonance structures, because we have 5 specific patterns. So, as we were talking about before, we have vinylic positions. So let's take that molecule we started out with from the very beginning. Actually, I think I want to draw that again. Okay, so we have this carbon here, and we have this carbon here. So for these carbons, these are both vinylic positions because they're directly attached to the pi bond. But if we take the same molecule and consider these positions, these carbons are next to the pi bond. So that's why we called it an allyl system. These are the allylic positions. So let's look at an example. So say we have this molecule right here. try and draw that one more time. So we can ask ourselves, are these allylic positions or not allylic? So this position right here, I mean, it's not really, it's not attached to a pi bond, and it's not near a pi bond really, so safe to say this is not allylic. This one, on the other hand, it's got the pi bond over here. It's next to it. So this one is allylic. Okay. So all the lone pairs, to draw the resonance structures, they should usually be allylic. So allylic carbocations, they only take one curved arrow to show its resonance. So let's take the initial example we were using from the beginning that started this whole debate. So it only takes one curved arrow, and that'll show us the positive charge on the left side and the pi bond on the right side. So that's pretty simple. But if there's multiple double bonds, then multiple contributors are possible. They're drawn by moving one electron pair at a time. You can't do multiple simultaneously. So that would look something like this. So we can move this one here. So that would give us plus charge right here now. And now we have a pi bond right here. Still have our other pi bond right here. But now we can actually move this pi bond to the deficient site. So then now we're going to have this one. We have a pi bond here, and the plus charge moves right here. So we can't do this last one, this last carbon here, because this one is already sp3 hybridized. So that's no good. So let's consider the next kind of resonance pattern. So what if we have a lone pair adjacent to a carbocation? So let's take this molecule, for instance. get in our lone pairs, and this is an ion, so it's negatively charged. This is positively charged. So only one arrow is needed for these kind of structures. This is for when a lone pair is adjacent to a carbocation. So if we just draw our arrow here, move it here, we'll form that pi bond in between the oxygen and the carbon. This will actually become zero formal charge, but those two formal charges on the initial structure are already equated to zero because they cancel each other out. So let's look at one more example. So if we have this structure, and suppose we have the plus charge right here, we only need one curved arrow, and we need to start from a lone pair. So we can go right here to the left. The next structure is going to look something like this. We have our pi bond here now. We have oxygen and the rest of the structure. The plus charge is now on oxygen. All right, so we have two more resonance patterns. We can have a pi bond between two atoms of differing electronegativity. So the pi bonds will be attracted to the more electronegative atom, causing the pi bond to be unequally shared. These two resonance structures represent the extreme depictions of the pi bonded electrons. So equally shared versus not shared. The actual compound, you know, as we've been saying all along, is a hybrid of the two. It's unequally shared. So let's look at this here. So because this molecule is polar, this oxygen is going to bear a partial negative charge, while this carbon here is going to bear a partial positive charge. So if we were to shift this, break this pi bond to create a lone pair on the oxygen, that would give you a formal charge of -1 on oxygen and a formal charge of +1 on this carbon here. So, and we always put brackets for the resonance structures. So one more pattern, and this one is, I mean, I think this one's fairly straightforward. It's conjugated pi bonds in a ring. So each atom in a ring has an unhybridized p orbital that can overlap with its neighbors. The pi bonds can be pushed over by one position, either clockwise or counterclockwise, doesn't matter. The result is the same. So let's take a benzene ring. And we have 3 pi bonds. So these ones require 3 arrows when it's a benzene ring. So this pi bond could shift here. This one could shift here. This one could shift here. And it would end up just moving to all those places of the head of where the head lands, or the head's pointing to, of the curved arrow. So we have one here, we'll have one here, and we'll have one here. And that's pretty much that for conjugated pi bonds in a ring. So let's go over each of the types of patterns of resonance that we talked about. The first one that we had was the allylic lone pair. So we had the allylic lone pair. So that was, we'll just use this example. So for allylic lone pairs, you need 2 curved arrows. Okay. The next one was the allylic carbocation. I'm just going to write plus in a circle. That represents carbocation. So that was this example. And we said these ones only require 1 curved arrow. Then we said lone pair adjacent to a carbocation. That was this example here. And these ones only require 1 curved arrow. Finally, we have those conjugated pi bonds enclosed in a ring. That's just where you have the benzene ring with 3 pi bonds and 3 arrows. So 3 arrows. All right on. So yeah, these are the 5 types of resonance patterns that you'll encounter all across pretty much after you cover this in your organic chemistry class, you're gonna potentially deal with these structures when a molecule is resonance stabilized for pretty much the remainder of your organic chemistry career. So yeah, I would definitely watch the next part 2 for more examples with these 5 patterns of resonance structures. Right on.